So welcome to my talk about feature-oriented visualization, and I brought you a short overview, so I will introduce the topic a little bit. I didn't know exactly what the audience knows, so if it gets boring, just tell me. I am sure I have some new stuff following on. I will show you how to study vertex burst as a physical phenomenon important in aerodynamics. Then we will turn to application actually coming from medicine. So we'll look at heart blood flow, for example. Then we'll do some things in climate analysis when we look at the Benguela upwelling system. And finally, also return a little bit to theory, where we use higher order moments, which you may know from image processing for scalar fields, and we extended this to vector data. So first of all, and shortly, and since you have a background there, what's visualization doing? Well, principally it takes digital data and transforms them into digital images using computer graphics. And the idea is to efficiently and precisely represent information about the data. You could also say it's a way of communicating digital data in an efficient manner to humans. So it's really that interface, the communication. That's the point here. And while we are dealing in the applications that I'm looking here today, mainly on continuous field data, so typical engineering simulations like fluid dynamics or climate production, the scientists use simulation data. And these simulations generate field data often given on a grid in 2 or 3 dimensions, and this may be time dependent and tends to be large. So a direct visualization of all the data is not possible, right? I have a few million pixels on the screen. We can debate if it's 1, 2, or 10, or 20 million, but there is a boundary even for your eyes. And if I have gigabytes of data, billions of data points or vectors, there's no way I put them on the screen. So I have to do something else. And the visualization community, the scientific visualization community in this area comes up with a pipeline approach, basically. It starts with the data, does some filtering. You can see it means selecting fields, smoothing interpolation are typically operations. Then the specific area here that's interesting me most, I have a mathematical background, is we try to do a data reduction on a mathematical basis before we do the central part of the visualization. That means you take the data and transform it into geometry and optical properties before you use the computer graphics rendering to generate the image. Of course, you can interact and that way get animations, get deeper into details that are of interest to you, and so on. What I use for the mathematical analysis are different kind of mathematical theories. And in terms of fluid dynamics applications, there is a relation between a mathematical theory called dynamical systems, which is also popular in certain areas of computer science, and actually fluid properties like vortex formation that are interesting in our hydrodynamics. So that's kind of the basic idea, and you see this is actually hand-drawn. It's a sketch, goes back, oh it doesn't say it, but to 83. So this is about, yeah, close to be 30 to 40 years old. So what is the idea of this topological analysis? So some very shortcut on dynamical systems just in 2D. Well, if this is a very simple academic flow, don't worry, we'll come to more complicated examples later, then I can, of course, take numerics and calculate streamlines. But the difficulty is, of course, I can draw millions, and if I will, billions of them. So the question is, how do I show you in a qualitative manner how all of them behave in an efficient way? Yeah, so the question here would be, at the moment, where do they start and where do they end? And in this example, if I look where do they start, I figure out all the streamlines over here start at that boundary, all the streamlines over here will start at that very point, and then there are 2 exceptional lines that make up this blue boundary. As a computer scientist, of course, if I have to calculate it, it looks natural to look for the blue curve because that gives me probably all the information. Yeah. If I turn the question around, who do they end? Well, this is a very simple example. Pretty much all streamlines end at the boundary except for these two exception lines who end over here. And if you're mathematically precise, well, there are these two dots where the flow is stationary. So if you start a particle there, it will just stay there all the time. And now I combine the two, pretty much an intersection. And then I see that I have lots of streamlines over here, and there's just one and another representative. They all start here and end over here. You have that part, upper part here, where the flow goes from here to here. You have the lower part that goes from here to here. And the interesting part for a computer scientist, of course, is I can calculate these zeros in the field. I can take the derivative of the vector field, figure out these directions, can integrate these four curves, and that essentially gives you all the information you wanted. And there's a nice mathematical theory behind it that, of course, tells me that this algorithm or this procedure is actually correct, and not only in one example. Yeah, and then I can go to the theory, and it tells me, well, where can streamlines start and end? It's at the zeros, at the critical points, at closed streamlines, at inflow or outflow regions. We have seen that. And if you go to 3 dimensions, then there are things like strange attractors, typically named as the Lorentz attractor or the Smale horseshoe. If you ever heard about these are typical examples here. And there are algorithms to kind of exactly or approximately find these structures so we can, for steady flows, structure the field from here. Why is this interesting in applications? Well, actually, sorry for taking a German car here. I could use a Toyota as well. What you could look at is if they build cars, they pre-calculate and simulate the airflow around the car. Yeah, because air resistance is a problem, especially for the fast cars. Yeah. And then you can project the flow near to the surface, on the surface, the so-called shear stress flow. You can do this analysis, and the blue curves are going to be white here, and you still see all these critical points. And then you can see that some of them are spiraling in. So you really have this motion of spiraling in on the surface. Of course, a physical flow is not going to concentrate on that one point. In fact, that is what the yellow lines show you. It's spiraling, but it's going away from the surface. So we have a vortex attached to the surface that we can find by our topological procedure. And that's what one of the things that's going to be interest. I could talk a little bit more about these problems, and we can talk about this over lunch, but let's turn to vortex bursts. Okay? And we stay with aerodynamics, but we go up into the air here. Well, first of all, vortex burst is a physical phenomenon, and of course there's a classroom experiment for that. And what you would do is, you take a can with a viscous fluid or cylinder and a small rotor behind here. Here you can see the actual physical experiment. And if you start rotating slowly, there will be a small kind of tube-like vortex, the kind of type that we all know from the bathroom. The interesting part is, if you start spinning faster, depending on the viscosity, at some point the shear creates strong deformations, so there's a rapid change, and yeah, it really suddenly looks completely different, the structure. As you can see here, this is not what you usually would observe in the bathroom. And that's what they call vortex burst. Basically, normally the velocity would go up here, but at that point it goes down on the major axis and has to go around. So it's an interesting phenomenon. And of course, the simulation can reproduce the experiment. Just do your numerical simulation, CFD simulation, based on the Navier-Stokes equations, because you have to take care of the viscosity. And critical points play a major role, so always zeros. Yeah, that's the way we want to attack the problem based on the algorithms. So the burst, and that determines the vertex burst. So I'm looking at the field over time and look where do the zeros appear. And we assume here, we could do that differently, that our field is defined on a tetrahedral grid. If it were different, we just have to do a little bit more. But then we assume that our field is piecewise linear in space and over time, and then we can find the critical points in all time steps. We can track them over time, even a precise measure, otherwise we had to do some numerics there. We detect the bifurcations. These are the points in time and space where these critical points appear, and then we can create a precise visualization. Let's stay with the Can for a second and forget about all the lines except for the green ones. We know in our very simple example, everything basically is taking place around the axis of the cylinder, essentially. So we just take the z-axis as the x-axis down here. Yeah, 0 will be the bottom, 1 will be the top of our can, bottom going to be here. And then we can look at all the time steps, and I see there are up to 5,000 of them. So even if that's a small can, you already get a lot of data. Yeah, because there are a few 10,000 data points here, gives you a vector for each of them, and then you times 5,000, so we're still looking at 50 to 100 million vectors here. And then I can calculate, okay, there are no zeros here, but exactly at that time step, at that height, these green line means there are two critical points created, and they are, the one is traveling south on the, to the bottom, the other stays pretty much at its height. There's a second appearing, and if I take a snapshot at that position, I can actually nicely see these two kind of structures. Yeah? And the zero pretty much means it should be spiraling up, but the velocity, the upward velocity, the velocity at all, is zero there. So it's going up, going down, yeah, and if there is flow going up, going down, the other flow has to go around. That's what's actually, if you look just at the fluid motion, yeah, what creates this bubble. And you can see nicely here how it behaves, and if we take a snapshot quite late, it looks like this one up there. And then we've been looking at some other variables that actually led the aerodynamicist here, the mechanical engineer, to speculate that the acceleration of the field creates zeros earlier. That's an observation. And then later he came up with a theory that that's actually the case. Of course, this is no theoretical proof, but yeah, there's a physicist in the room, right? You have to have the observation, the idea, and then you see if this is an artifact, yeah, if that appears all the time, you don't believe it's an artifact, yeah, and then you start to look down to your theory, but for the theory you need that starting point. Yeah, and that's what visualization can do at its best. I promised you to look at something more serious. This is a delta wing, and it's a famous shape for building very fast airplanes, especially also for military purposes. And so we work together here with the DLR, that's the German Center for Aerospace and Aerodynamics. And we have the air wing, and you can see there's a high angle of attack. Pretty much in the simulation, you fix the grid, you fix the plane, and then you have the air coming in, like you have in a wind tunnel, which is the same physically as if that wing is moving to the air. And there's a difference, you see that angle here. The case is, it's moving in this direction, but it's pointing in another one because the airplane is taking a curve, yeah? And then you see this nice vortices here, and you see we're looking at a case where we actually have this vortex burst that happens up here. And this is well known in aerodynamics that this is a very sensitive case. It can look like this rather nice shape, or like this chaotic, and this is very sensitive to that. So whenever I talk to fluid dynamics people, they're quite fascinated that we can see that, and they're also interested in what I show you now, because